So we were talking about the what we were talking. We were talking about the last time I end up. I think I passed the fixed point. I done this. Yes. Chaos and the period window. Did I talk about chaos and the period window?
Yes, you did.
Yeah.
I did that.
I think we stopped right after that.
I think we were just at the beginning of analytical analysis, right?
Yes.
Okay, let's just start here then. Analysis. All right. So we did some of this analysis. I think. Before the spring break, but we're just going to repeat some of this. So so if we consider the logistic map, and again we simply say fixed point. Fixed point, of course, is simply determined by x star equal to fx star. Then there's two to your fixed point, x star equal to 0, x star equal to 1 minus 1 over r, just solving that equation. And then the stability of the fixed point are determined by the multiplier. So multiplier simply say we're taking the derivative of the map and evaluate the fixed point. So from this is kind of trivial. You can say if you, for example, for the first fixed point, x star equal to 0, you're taking derivative of that, which is r minus 2rx. Evaluate this at the x equal to 0, give you r. Therefore, the 0 fixed point is stable if r is less than 1, and it's unstable if r is greater than 1. Right? It's greater than 1. So right. Now, for another fixed point, the one which is at 1 minus 1 over r, if we evaluate f prime x star, then it gives you 2 minus r. So therefore, this fixed point will be stable if r is greater than 1 and r is less than 3. Right? Because when r is greater than 3, the magnitude of this thing is become greater than 3, then become unstable. So that's actually is analytically where the periodic doubling happens, that at r equal to 3. So here is a graphic way to look at it. We're plotting here. This is again xn plus 1 equal to xn, and this is a logistic map itself. So when we change r, I simply change this height of this peak. So therefore, the slope near this point keep changing, and of course, if the slope is less than 1, which is this line, then this is only fixed point. So this is only fixed point. Right? If the slope is less than 1, it's only fixed point. And as r increase, once r increase across the 1, then we have a new fixed point, which is here, the second fixed point. And this fixed point, and then once of course this r is greater than 1, this fixed point becomes unstable because slope here now is greater than 1, the slope of a map. And the slope of the map here will be less than 1 until r approaching 3. So when r keep increasing, this peak keep going up, and then at certain r value, this slope, which is negative actually, become a great magnitude-wise, become greater than 1, then this becomes unstable. So it's graphically very clear. Now, once it's beyond r equal to 3, then the system develop is no longer this both a fixed point, both these two fixed points are no longer fixed, well, are no longer stable, So both are unstable. Then what will happen is we develop period doubling. Period doubling basically say is a, well, I think we have done here. So we have two value P and Q. So if mapping of P equal to Q and the mapping of Q equal to P, therefore if we map twice, so map P once, map P another time, then it come back cell. So therefore the P and the Q are actually fixed point of the F square map, right? The Q and P are fixed point of F square map, or what we call second iterative map, the second iterative map. So here's a shorthand notation. So basically we map twice, we just write in F square map. Now, if we plot this function, the F square map, you notice then once the R is greater than 3, you develop this two fixed point, which is P and Q. Now, the original fixed point, 0 and 1 minus 1 over R, is also fixed points of the square map or second iterative map, right? Because if it's fixed point of original map, then obviously it's a fixed point of the second iteration, because you iterate twice, it still go back south. So, but what happened is those two are unstable, and then once R cross 3, you develop two new fixed points for like F square map. And I have my Jupyter note. I need to switch. Okay, here's. So here is let's say it's not here, not here. Okay, so what I have here is, so let me. Are you seeing my logistic map Jupyter Lab?
Yes.
Okay. So let's say 3. Let me say 2.5. 2.5, and the map itself is still a logistic map. I gave you a bunch of well, let's just simply try to plot the curve. So xn1 is original map. xn2, you notice I map it twice, right? I map it twice. So this is a f square. Then xn3 is f cubed, which I will come to later, which had to do with periodic 3. So let me plot just xn2. Okay, let me run this. So yeah, so this is the case where yeah, so where's the original map? I want to xn, well, let me put xn1, okay, here you go. So this is the orange is the original map, right? And the green is the map square, or f square. So you can see for r equal to 2.5, they're just these two fixed points, right? 0 and so of course this fixed point is a fixed point of original map. It's also a fixed point of map square, right? And if I choose some initial value, I did not plot this co-web construction here because it's just gone too busy. And you just get, you know, end up with this stable fixed point in last 50 iteration. Now, if I change it to say, for example, close to 3, then you can see this f square map now is developing a slope here, which is now very close to 1. Once it cross 3, this seems bend this way, here bend this way, and you're going to develop two new fixed points. So let's try 3.1 example. And then you can see that then now there's one fixed point here, one fixed point there. Okay, that's one fixed point here, one fixed point there. And then the value will be, there's two possible of value. Let me just blow up this a little bit. So let's do 3.3, for example. It should be a little bit more clear. Right. You see now clearly, right? There's a fixed point here and a fixed point there. And if you, for any kind of initial condition, you will end up basically cycling between these two. And here's a plot of what I have here is how many iterations? I have 400 iterations. Let me just do 200 iteration, and let me show the co-web construction. And all right, so here's a co-web construction. So you see the co-web construction is at end, basically it's basically cycle between these 2 points, this point and this point. And you can see this is just periodic. So this is a periodic two window of this. So the system undergoing periodic doubling. So if we now look at the what do we call, this is a kind of bifurcation diagram, which sometimes we refer to bifurcation diagram. This also, namely, or in the book, it's called orbit diagram. So what we're showing here is the fixed point as a function of R value, is R value. So if R is less than 3, there's only one fixed point, stable fixed point. If R is greater than 3, then I get periodic doubling. So the value basically keep jumping between these two. Now the color in this graph I generate is labeled by the even R. So one color is even, one color is odd. So basically that means it's keep jumping between these two.
Question real quick.
Yes.
Is there a reason in general? So for example here, like when the 4-point cycle becomes stable, the 2-point cycle becomes unstable?
Yes.
Does that always have to happen, or could you have like a stable 2-point cycle and a stable 4-point cycle simultaneously, and like initial conditions would determine which one you get sucked into?
No, because you remember when we go back to the earlier chapter when we talk about a bifurcation. Take this example. Here is a one stable fixed point, and then at the bifurcation point, the original stable fixed point become unstable, which I did not plot. So this fixed point is still there, but it's unstable. And then you develop these two new fixed point, which is stable. So this is you remember, it's look exactly like a supercritical bifurcation, like supercritical bifurcation, and it's always alternate between. It's always had to alternate. The fixed point had to be alternate between stable, unstable, stable, unstable. So you could not maintain the original stable fixed point because the topology does not allow you to do that.
They don't have to alternate in maps though, right?
Well, if you look at this map itself, right? So if this is so let's look at this square map, this green curve, right? So this is unstable fixed point, and it's coming back. So that means the slope here is greater than 1. It's come back, and then it's intersect with this 1. So this slope is less than 1, so therefore this is a stable fixed point. And then as you going on, so once it's less than 1, if you want to cross back again for another new fixed point, you are guaranteed topologically this slope had to be greater than 1 in order for this curve to cross with this diagonal curve.
Right, you can't have two stable.
So you cannot, yeah. So right. This must be unstable. And then once you cross unstable, if you want to have another fixed point, that means this had to be bending down, cross this diagonal again, and that's basically say guaranteed this slope had to be unstable. I mean, it had to be stable because here is a slope of 1. Then you coming back, it had to be slope OG is coming back. That's well, actually coming back is actually it's not obvious. I can go all the way up and come back in a very steep curve. Then this could be unstable, is that right?
Yeah, I think we decided you could have two unstable fixed points next to each other, but you could never have two stable.
You cannot
fixed
have
points.
two stable fixed points, right?
Yeah,
because that's true. Because imagine you have two stable fixed points, then and you think about the value in between, you don't know which way to go, right? So let's say I have this fixed point stable, this fixed point stable. Then on the flow diagram, some of this value must be flow this way, some of them will flow on this way. There must be a dividing point, which to the left they flow to the left, to the right flow to the right, and therefore there must be a unstable fixed point in the middle. Right. So that I think that's a good question. Yes, please ask question periodically, because if you don't ask question periodically, I just don't have any feedback. I don't know what's going on. Okay, very good. So okay. So we say if now I do this say r equals 3, 3, and I have this say I develop two new fixed point, and if we look at that bifurcation diagram, orbit diagram. So this whole thing will bifurcation again at this another value. So from period 2 to period 4. Now, up to period 4, you can still doing analytically. I think beyond period 4, it's become incheckable algebraically to do analytical questions. So let's say, so here it is the period 2. So we develop these two new fixed points. Now we can analyze the stability analytically for these two fixed points. Actually obtain value of r, these two will be still stable. So the way we do that is, okay, is first we find analytically what is fixed point. Because fixed point is simply take f square x, set f square x equal to x, or f square x minus x equal to 0. This give you a quadratic equation, namely the force power, polynomial force power, which in general is there's no analytical expression for that. But since we already know two fixed points, namely these two, so you can factor these two out, and then what will remain is a quadratic equation. And the quadratic equation, you can solve it, and the solution is given, then solution is given by these two values, P and the Q. So there are two values. Because a period doubling, so there's two values. And you can see there's a square roots here. Square roots are minus 3, are plus 1. So this square roots underneath this thing, once r is greater, so this only exists when r is greater than 3. See, this fixed point only exists when r is greater than 3. So that's why two cycles exist for r greater than 3. Now, for its stability, for the stability analysis, we want to show that period 2 cycle is stable between these two values. So how we analyze stability? So stability of the period 2 double is equivalent to the stability of fixed point of f square map or double map, right? So because P and Q are fixed point of this map function, so you just treat this f square as a new map and calculate its multiplier. So basically say we calculate multiplier of the f square map, which is f and fx. And this you do the chain rule when you calculate derivative. So you do chain rule of this things. So it's f prime, fp, and f prime p. Right? So you take a derivative of this, and then inside bring out, you take another derivative that gives you. And this whole thing evaluate xp. Well, since fp is give you q, so therefore this equal the product of f prime q, f prime p. Well, this can be evaluated analytically because both of these quantity are fairly, and we already know the Q and the P value, so we can plug in and they can find out. So here is algebra. I won't go through that. So if you plug in those Q and the P value, you get this. You get this value. Okay. After carrying out differentiation substituting P and Q, you get this. And this is a quadratic equation. And we can decide when it's greater than 1 and when it's less than 1. So it will be stable if this value, the multiplier, is less than 1. And since it's quadratic equation, you can solve it, this inequality, and you find that R is this multiplier lambda is less than 1 if R is greater than 3 and less than 1 plus square root of 6. Less than 1 plus square root 6. And you calculate 1 plus square root 6, that will be, so here's, so you have between R and 1 and 3, that's one fixed point. Between 3 and 1 plus square root 6, you get period doubling. Beyond 1 plus square root 6, you get period doubling again. And this, let's look at my notebook. So same thing, it's this point. So, and they are square roots of 1 plus square root 6 is this number, 3.44948. So you can see that's as we approach that number. So let me plot this again. This is 3.4. You can see you still have nice periodic behavior. Now let me get rid of some of these things so we can. Too many curves here. Let me now do this. Only plot the square map. Now let's go to 3.45. So this is just 3 digit. Is this just at the where the period doubling happened again? So you can see this just go a little bit beyond it. Now I have, if you look at the iteration map, so it's 1, 2, 3, 4, 1, 2, 3, 4. So 4 value. So in fact, 1, 2, 3, 4, 1, 2, 3, 4. And basically, what happened is the slope of this square map here, slope square map here, where there's a fixed point, is become greater than 1. So original fixed point of a square map or second iteration map become unstable, and then the well, those two become unstable for the square map, but it becomes stable for the fourth iteration map. So if I do following, let's say if I do square map, let's do fourth iteration map. So let's say 4. So I map this 4 times. And let me not put the covert diagram on. Oh, to X and X4. Yeah, so here is the orange one is a second iteration map, and this fixed point, which is where this point is, the slope now you can see the slope is greater than 1, so it becomes unstable. While the fourth iteration map, which is the green curve here, now develop a nearby 2 fixed point. Okay, similarly here, there's a 2 new fixed point here. Now for the fourth iteration map, and if I just do this a little bit bigger, probably you'll be able to see it more clearly. So you can see that there is 2 fixed map, and that's what it happened here. So, and let's say if you look at the bifurcation diagram, it just keep going. So you get period doubling again, and doubling again. So in fact, if I zoom in this part of the orbit diagram, so which is now I'm zooming here. So this part will be something around the 0.85, and between 3.4 and the 3.6. So between 3.4, between 3.8, the 0.8 and the 1.0, and aspect ratio 1. Let's see. It's not returning.
Apparently it's still working.
It's still running, I guess.
Yes.
Do I need to run? Okay, there you go. Yeah. So you can see I'm zooming between 3.4 and 3.6, and only a small part of value, so between 0.8 and 1. So if you're zooming into this small region, it looks like exactly like original one. You know, that particular orbit here become period doubling again at this particular 3.448 something, at this point, and then it's doubling here again and double. And if you zoom in any of this place, it look like exactly the same. So this is a property of an object, which when you zooming at the small scale, is looking at larger scale. And that's a particular terminology for this. This is what we call fractal. And we'll come back to discuss fractal in the next chapter. We'll devote a whole chapter to talk about fractal, namely an object which has non-integer dimension. Object has non-integer dimension. So this object is clearly does not have dimension 2, but it's greater than dimension 1. So it's somewhere this object has a dimension which is between 1 and 2. So called fractal. We'll come back to talk about fractal in the next chapter. But this period doubling, you know, it just keep going, and then of course the successive doubling, this interval becomes smaller, and eventually converge. Eventually converge to a limit, and beyond that particular limit, the system becomes chaotic, which is so here is, so this is now zooming out to back to a larger R value. So like it's happened the chaotic in here, and those number, which we mentioned already earlier. So go all the way. Oh, I'm doing too fast. So if you go all the way, when we initiate, yeah. So here, so it's a 3 period doubling, 3, 4, 4, 9 period doubling again, and they keep period doubling until you reach the limit number. 3 point. Of course, we cannot find this limit number in analytically. Just numerically, we have value for these things, and so you can see once beyond this, the system, the attractor is no longer can be described as a period doubling. It's got infinite number of a point, where the attractor has infinite. It's a set of infinite number of points, and it's jumping around just between those two. Now we call that system, we call that object chaotic object. And the question is, what do you mean by chaotic? Like chaotic. Now, do you remember, guys, how we define chaotic?
Not really.
Any of the other people? How we define objects chaotic?
There's 3 things: aperiodic, sensitivity to initial conditions, and something else.
Yeah, so it's not a periodic. Number one is, so therefore there's no fixed point. And what important is a sensitivity to the initial condition. What is a sensitivity to initial condition means? Ray? You hear me?
Oh, yeah.
Yeah. What is sensitivity to initial condition means?
Means like a small change can lead to a greater change in the future?
Yeah, a small change. Yeah, a small change initially lead to greater change. In fact, namely, you say if initial point dynamic system has a small change of the certain number of iteration or certain number of time. In this case, a certain number of iteration, the change is no longer predictable. Namely, it cannot be predictable because the things just grow exponentially big. So we're going to have a little bit later to talk about the how we describe quantitatively chaotic behavior. But come back to this bifurcation diagram. What you notice is that, so we have been discussed so far all the way 3.4 all the way to this limit where it's first transition to chaos. And we'll come back to discuss what exactly the chaos is. But if you look at globally, there's another interesting phenomena. You notice, you see there are this window where the systems are not chaotic. And this is called the window of periodic behavior. So for example, this largest window is around here, around around 3.85. Right, this is 3.8, this is 8.5, here's 9. Around 3.8, you see there is a period 3 orbit, right? Because 1, 2, 3, 1, 2, 3. So there is a window of this period orbit. So it's not like beyond this R value, everything is chaotic. Most of this chaotic, but in this chaotic, overall chaotic regime, there are window of order behavior. So we say there's a window of ordering in the chaotic behavior. So there's a window of ordering. So that's window ordering. And in fact, if you just blow up, for example, this region, which is you blow up one of this region. So I think this is a blow up. Actually, probably this region, blow up this region. Yeah, it's blow up this region. You find out that its behavior look like qualitative, exactly the same thing. There's a periodic doubling and length. It is at a certain limit, it transitions to chaos. And in this chaotic region, again, you know, remember this portion is just a teeny portion of this figure right here. And so you blow all this area up, again, there are windows. There are windows of ordering, a window of periodic behavior. So let's just demonstrate this by, for us, we can look at so the window of behavior is along between 3.8 and 3.9. So, so I zoom. Let me zoom between 3.8 and 3.9, and still.
You did 3.69.
Oh, thank you. 3.9. So that's zooming on that portion of the graph. It will take a minute or so to run this things. Oh, actually, I have the here. I get this long, so this aspect ratio. Let me just stop that one. Stop this one. This should be 0.1. It's a little bit tricky to. So anyway, I run this last night. So it's between 3.8, 3.9, and that's what it is. Right. So You see the R value is between 3.8 and 3.9. There's this window of period 3. And if you look carefully, this inside this window period 3, this whole thing just look like larger bifurcation diagram. It just looked like this the bigger diagram, the bifurcation diagram or orbit diagram. And if you zoom in here, each of these individual, then the whole thing just repeats itself. It just repeats itself. And here just to show that indeed we have a period 3. So now I'm doing period 3. So I do 3 times the map. So that should be a fixed point for period 3. Oh, I should plot 3, not 4. Yeah. So the orange curve is a map square. The green curve is a map cubic. So so you can see for this particular R value, which is 3.45, then a cubic map only have one fixed point, which is the same as the map itself. Now, as I increase R value to 3. I believe it's around 3.82. So you can see this green map. You know, basically this is this quadratic minimum. It keep coming down as increase R value and close to 3.82, it start to touching this diagonal curve. Once it touches the diagonal curve, then you develop period 3. So at the moment, it's not quite there yet, and you notice that the behavior of iteration map itself is just chaotic. You know, it looked like you're trying to get a period 3, but it cannot quite hold it on period 3, and then it berserk. It go go to some other value, and it try to. So this is called intermittency. And so let's say let's go close to this value. So 8 to 8 to 8. So maybe 8 to 9. This will be period 3. Now you can see, yeah. So this is just a little bit beyond that the value. So now all these 3 lobes touch. Now I develop period 3. So in fact, I don't know, you cannot quite see. It look like period 2, but in fact it's a period 3. So 1, 2, 3 value. So in fact, let me just, instead plotting last 50 point, let me just plotting 10 point, for example. Yeah, so it's 1, 2, 3, and then 1, 2, 3, and 1, 2, 3. So it's basically 1, 2, 3, and 1, 2, 3, 1, 2, 3. So so you have period 3 window, And if you just go beyond a little bit, this, you know, it's very sensitive. If you go a little bit more, let's say a 4, then you back to chaotic behavior, presumably. Well, it's still period 3. Okay. Maybe I need to plot more point. 50. Huh? Where is that window of become chaos? So 3.84 is still. If I go to something like A5, 855, I think it should be chaotic. So let's say 855. It doesn't look like chaotic, does it?
No. Well, actually, it does look a little bit different, but that might just be my eyes.
Let me just look at this, where it is. A5 is here.
Like the if you scroll up a little bit, it might be intersecting with the other.
Yeah, maybe it
points.
happened to run into some reason. Let's just call.
And
this,
like the chaos or whatever might be in like just the small deviations between.
Let me just change a little bit more value. So if I where this, I probably need to plot more point to see long-term behavior. Let's plot the 100 point. Yeah, so you can see this is at A6. Those fixed point, which is it was in for the period 3, is no longer stable, and the system becomes this called intermittency, and then intermittency to the so it's trying to get the periodic behavior, but it's couldn't try. It really cannot get. So this is the intermittency behavior, intermittency behavior. So that's qualitatively. Now analytically, let's go back to analytically. Let's now look at the so we did that. We did this. So we say there is a periodic window. There are periodic window. So so F3, for example, has a period 3. So this is exactly what we just did a minute ago. And intermittency is basically, so if you look at this xn as function of n, it's look like trying to be periodic, but it cannot quite hold it. And then, you know, you get some kind of look like random behavior, and then it's trying to be periodic. And that is because if you look at this curve, in this intermittent regime, it's not quite there, but if you zoom up here, you see there's a small channel. You know, when you're stuck in this channel in the covert construction, in this area, it look like periodic. It look like periodic. It look like periodic, but it's not quite, because this actually did not intersect. So those are intermittency regime, intermittency regime. So intermittency is not just a curiosity logistic map. It arises commonly in systems where the transition from periodic to chaotic behavior take place by saddle node bifurcation. So the bifurcation we so far is a saddle node bifurcation. You keep bifurcating, and they go to chaotic behavior. Now, experimentally, in fact, intermittency is often observed. Intermittency appears as nearly periodic motion, interrupted but occasionally irregularly fast. In fact, people have done some laser experiment. This particular route to chaos is called intermittency route to chaos. So here is actually a oscillation of laser power at certain controlling parameter is periodic oscillation, and as you change the parameter, so this is as you change the parameter, then it go to intermittency regime. As you further change the parameter, then it becomes chaotic. So you actually this are observed in number of experiment systems. So. And of course, inside that window, again, you have this period doubling behavior. Okay, so that is about the window of order inside the chaos. And now we're going to come to talk about the how to quantitatively describe the chaotic behavior. So the number we use to describe the chaotic object quantitatively is what we call Liapunov exponents. So how do we know whether the system is really chaotic or not? Again, so Luis said earlier, it's a sensitivity dependence on the initial condition and the initial condition. So we want to make this qualitative statement now quantitative. So quantitatively say, let's given a initial condition x0, and consider a nearby point, a very close by, so a small deviation from x0, delta n is a small quantity. And then we iterate this two initial condition n time. After n time iteration, then the delta n be the separation between after n iteration. So delta 0 is the initial separation. Both of them iterate one time, you get delta 1, and so on and so forth. So delta n, in general, if it's sensitive to initial condition, this delta n will be proportional to the initial separation, and then it will grow exponentially. It will grow exponentially. So as e to the n lambda power. Now it's only grow exponentially, of course, if this lambda quantity is a positive. If lambda quantity is a negative, then the separation becomes exponentially decreasing. That means it's a stable behavior. So, and this is how we define a Liapunov exponent. So it's by examining the sensitivity to the initial condition, So a positive Liapunov exponent is a signature of chaos. So here now we have a quantity which can be quantified chaotic, and small lambda is chaotic, but a large lambda will be more chaotic. So you can actually quantify it. Now to calculate this lambda is numerically is very easy. You just do it n times iteration. All right, with a small deviation for the initial condition, you calculate the separation, and if it's grow like this, logarithm, like exponentially, then of course you take a log, you take a ratio of delta n to delta naught and take a log of that and divide by n, that give you lambda value, that give you the lambda value. So these things can be calculated numerically fairly easily. In fact, I'm going to give assignment to ask you to calculate this lambda for a couple of math. All right, so this delta n, of course, by definition, is a difference between an nth iteration, the separation, and this difference, of course, if you take delta not equal to 0, then this is simply the derivative function, right? This is definitive derivative function of this nth iteration map. This is fn power taking derivative and then evaluate at x0 if I take delta not equal to 0. Now notice that the object is finite, so in order to calculate numerical calculation quantity like this, you need to take initial delta not small enough so when this separation can grow. If your initial separation is big, and then after a couple of iterations that the separation is already as big as the object itself, then this numerical calculation may not be accurate. So to numerically calculate these things, you basically need a sufficient number of n iterations where these things can change. Then you plot a linear curve of this delta n over delta naught log of this quantity as a function of n. Then it's proportional n. You get slope of that. So you basically plot log delta n over delta naught as a function of n. It should be linearly proportional to n, and the slope of that is what is lambda. So this fn prime, nth iteration prime, and then derivative, of course, by chain rule, you can rewrite in this fashion because fn after all is f nth of a mapping. So therefore, by chain rule, you can rewrite in this fashion. It's just like what we did with periodic doubling case. We get f prime p and f prime q, and it's just n times that. So if f prime x0, f prime x1, f prime x2, and so on and so forth, product n times of product listings. So therefore, if we substitute this into here, then lambda is given by this formula, lambda given from, and log of product can be converted to sum of log, right? That's the logarithmic function. So therefore, this lambda, for simplicity, can be evaluated. So this is one way to evaluate lambda is through this formula. You take an initial x0, and if you can calculate f prime, and if you calculate sufficient number of iteration, you take a product of this, since that gives you lambda. So let's provide an analytical way to calculate Liapunov's for certain map. So given by this formula, and here is an example. So a simple example is suppose Fs is a stable p cycle containing point n naught. Show that Liapunov exponent is less than 0 if the cycle is super stable and the lambda actually go to infinity. So if it's a fixed point, then Liapunov is less than 0 if a stable fixed point. And this, well, I will skip this since basically it's fairly straightforward algebra. Instead, I want to look at this second example, which is a time map. Time map is actually very similar to logistic map. So basically, instead, logistic map, remember, is some kind of parabola like this. But time map is simply say, I make this a triangle. So that's what it is. This is a tank. It looks like a tank. It looks like tank. So it's going up and down. And so it's very simple. The derivative of this function is either r or minus r. So this makes it very easy to calculate. So fx is rx on the left half and r minus r on the right half. So the derivative of this f prime, it will be either r or minus r, depending on what is left part and half. But the absolute value, therefore, is all r. So therefore, we can, so f prime is always r. Therefore, the Liapunov exponents, which can be calculated through this quantity, is simply log r, because each of these quantities is r, and you have n of this quantity and n divided by n, so it's r. So therefore, for the time map, if r is certain value, I'm going to ask one of you guys, since you've been so quiet. What I'm going to ask this time. C. C. Fam? Are you
He
there?
coughed in response.
Huh?
He's here.
Yeah. Is your speaker not working?
I think it's
Okay, now I hear you. Wait a second. Your voice? Are you talking?
yes.
Okay. So I'm asking you to say what's the question I want to ask now? Log r. So the question is, for what r value is a stable? I mean, it's a chaotic, and what r value is a stable? Well, actually, what do you think, Dan? Are you looking this?
Yeah.
Yeah. So you say the map is chaotic for r greater than 1 because lambda is log r. Remember, for chaotic behavior, lambda is greater than 1. If lambda is less, not greater than 1. Lambda is greater than 0. Right? If a positive exponents, they seem to keep growing. If it's negative exponents, seems to keep shrinking.
Increasing.
Yeah. So therefore, if r is greater than 1, log r will be positive. So therefore, it will be chaotic. If r is less than 1, then log r will be negative, and then it will be stable. So that is the case for 10 lab. And in fact, you guys should try out this 10 map. 10 map is simple enough to try it out. One can, for logistic map, you cannot calculate this lambda analytically, but you can calculate numerically, and that would be one assignment to calculate lambda numerically for logistic map. So here is actually calculation of lambda for logistic map. You can notice that in all this periodic regime, lambda is a negative. And here you get to this point where lambda cross. So this is the point where the lambda cross from negative to positive. And in So in this region, then is all chaotic behavior because lambda great. But in the chaotic region, you can see this window of periodic behavior. So for example, here is the window of period 3. So lambda go back to negative. So there is this window of period 3 and it's a stable. It's stable. But if you zoom in this region, you can see that it's again, it will transition to chaos in this region, very much similar like this region. So one assignment is to actually to reproducing this graph, to reducing this graph. Okay, I think this is a good time for me to stop because there's one more section in this chapter I talk about universality, and we'll come back to talk about that next Tuesday. Any of you guys have questions? Good.
I do not think so. Actually, hang on a second. Give me a second. Let me see if I can't find a question. Oh yeah. Okay. So I guess if you're trying to like prove something is chaotic or whatever, like how can you rely on like some sort of numerical type thing, you know? Because like if the amount of iterations that you choose are just so happen to link up with some sort of period, like by chance, you know?
Well, I think this is just to say to the limit of your numerical calculation is chaotic. It's not analytical proof, right? So
Okay.
if we look this, okay, I take a particular lambda value, and I just take particular R value, I calculate lambda numerically up to 1 million digits or something like that, and it is just it still give you its convergence. I mean, you can let's mathematically say as you keep increasing number of iteration calculate, the number converge to a number. It looks like the number is not changing, and that will be all you can do. It's just like to say how you show pi is an irrational number. Pi, you just can calculate certain number of digits. I don't know there's any analytical way to show that pi is an irrational number. You can just say, as long as the number digit you calculate it's not repeating itself, so it's irrational. Here, basically the same thing. It's to the numerical your capability of calculation. This lambda is a positive, so therefore that is in the chaotic regime. I guess that's all we can do. Yes. Okay. Well, if you guys don't have any other questions, that will be wrapping up to today's lecture. And I'm going to post, I'm going to post assignment for this chapter after today. Sometimes today, I need to do a little modification. The video I need to figure out how to upload to the YouTube. But I guess you guys, I don't think you want to watch my video again. But but I think the department probably want me to do that. So they just want to make sure. I mean, for our class, I think this is actually its idea for our class with a small number of students. I don't know. Any of you haven't taken a larger class yet online, right? It's starting next week, right?
Yes.
I'm really curious how that will go for larger. Any of you taking a larger class?
Yes. I don't know how to go either.
What class you're taking?
English specifically.
Oh, that's
So,
even more interesting. A large English class.
Yes. And
any other you? Thea and Ray, any large class you're taking?
Yeah, I'm taking
math, so they just post all the notes online, I guess. It's
they post the slide online.
They changed it to a flipped class, so It's like we read the note.
Ooh.
I mean, that's what they say. So, and then they record the lecture. And
Wait a second. How this can be do a flipped class online? I would think a lecture is more doable online, but flipped class is about to be a lot of discussion, right?
yeah, so I don't know how it's going to work.
Okay,
either.
so I'm really curious because I want to know. I'm getting lucky this semester. I teach a small class. But, last semester, for example, I teach physics 118, and that has 280 students, and I don't know how that transition to online will go. And it's also not clear. Any of you taking the lab class?
Yeah, I'm in the
Chemistry.
281 or whatever of physics. Like I haven't been looking at the stuff for that, but yeah, I don't know how. I think they're going to do the experiment for
and
us
the studio
or
thing
something.
will go. So this will be quite challenging for everybody. But if we all pull this off, maybe in the future a lot of this class will go online. At least hurricane and a snow day, we can continue teaching.
Yes,
There will be less disruption.
ideally.
Okay. Well, good to see you guys, and keep safe. And you know it's very important for you young people not going out, right? So
Yes,
so you don't care, don't
it's
accidentally
for
transmit
it's
it
for
to your
all of
parents.
us. It's for
Yes.
you.
Okay, it's for me. Yes, for me, for my generation. Okay. All right.
Have a good
Have
weekend.
a good day. I'll see you again next week.
See you guys.
Bye-bye.
Bye.
Bye.